Good afternoon, this is Schweitzer, and this is a little video on tutorial video on sort of a level 1 proficiency in vectors. So our main standards, can I add two vectors together giving a directional or absolute name? Alright, so as we get started again, this is more of a tutorial on this topic, and then we'll have some proficiency questions coming up. But a few things I'm going to point out to you that would be providing in-class notes. One is we have essentially here we have the Cartesian plane. Make sure you know we have east, north, west, south. To the right is a positive value. That's important. Positive I, J, and negative I, negative J. So this indicates the direction. Down is negative, to the left is negative. And then of course we have our degrees. 0, 90, 180, 270, and 360. This is the XY plane. So I tip this thing here and flip it flat, and then have it up for the Z, and then it's a positive K, and they're down into the ground potentially would be a Z or a negative K, which should be a negative Z. Keep in mind every vector must have a magnitude and a direction. So a vector must have a magnitude and a direction. Now, a direction has to be relative to something. You can't just be traveling, 10 degrees. 10 degrees to what? 10 degrees left, left or right, or it has to be relative to something. All right, so here, again, we're adding vectors together that are in giving a directional and absolute name. So here I have a tug of war, two tug of war teams pull on a rope. Of course, tug of war, you know that one simply pulls the rope one way and the other one pulls it the other way. The flattest, it would be flat, but whatever, you get the idea. You could say this one pulls it west, this one pulls it east, and they're pulling in opposite directions. Okay, so east and west. There's the middle point. East, so that'd be west and east. All right, so in this situation, it says Team A pulls, so it says 50 newtons to 180 degrees. So whenever we're dealing with absolute, this is a good example of absolute. Everything's based off east. So I can say this thing is, there we go, that is the 180 degrees. So this is an example of a 180 degrees absolute angle. And then it's pulling in the direction of 50 newtons. And then this one is 45 newtons. All right, and Newton is a force, which is a form of a vector, okay, because it has a magnitude and direction. And this one's going east. Add the two together, and I'm going to get 5 newtons, and it's just going to be to the left or west. You could just simply say west, or you could say 180 degrees. Okay. There's my answer. Okay, so 5 newtons west or 5 newtons at 180 degrees. And there's a vector showing that. Keep in mind, adding and subtracting vectors is something that we've done before typically. So this is more of how we give it a name and a direction. Okay. All right, next one. All right, so we have, all right, a little different question. A person walks 9 miles west and 2 miles north. So this is what we consider a baseline level 1 problem. All right, so let's walk through how we would do this problem and learn a little bit about adding vectors. Now, the only difference between this problem and the previous problem is that they're not directly in line. So we have to do a little math. Now, there are several ways to add vectors, and one of them would be to do it manually. So I'm going to, the very first thing I'm going to do here is I'm going to try and see if I can get an idea of where this thing is. All right, so 9 miles west. So that's my first vector. So I'm just going to take and draw this thing. We'll pick a different color here. All right, so I'm at 9 miles west. There we go. Now, to the left, just so you know, one thing that causes kids issues, they forget, it's a -9. All right, that's what that means. So the negative means to the left. 2 miles north. Now, whenever I'm putting together vectors, it's always heads to tails. So this head has with the tail of the second vector. So it goes up. Why is it going up? Because it's going north. And this would be a +2. All right? And then, of course, the resultant vector is the tail to the head of the next vector. Now, I didn't draw these two proportions. That probably should be a little shorter. That's fine. Well, just pretend it's a little shorter. All right, now, the length of this line is my actual resultant. So we call this resultant. That's the total new vector. This angle right here is the angle that we're going to be looking at. Okay, or I could have drawn it up and over. So this also could be an angle as well. So we'll talk about that in a moment here. So either way, how do I do it manually? Well, manually, I could just literally take a protractor out here, but I have to do it to scale at that point. All right, I have to have a scale for the length of my lines. 9 might equal 9 centimeters, 2 equal 2 centimeters, and then I actually measure the length of this line and the angle. Now, this angle right here is north. Okay, it's north of the west point, north of west. That's this angle right here. This angle is to the west of the north. So think about how we describe that. We're always describing our line relative to the west line or relative to the north line. The line that's the two lines that are between it. If I'm over here, then this is going to be, this angle would be east of south. This angle right here is south of east. That's how we do that. Okay, so think about that for a little bit. All right, so how do I get this thing, how do I go about doing this? Now let's look at a mathematical method. So I can do it manually by actually physically doing it on graph paper. Not as common for us. All right, so what do? First things first, it is super important to just kind of sketch out where are we going. We're going to the left, 9. So a -9. That's real important right here. And then we're going up 2, +2. So that dashed line right here is my new resultant. Now again, if I'm to scale, I could actually measure the length of that line and apply it to a scale. But at this point, I'm going to use a little bit of math. Okay. This is a right triangle. Now what's unique about this particular problem is that my two vectors are at 90 degrees to each other. That's a pretty important point here. Well, this is a 90-degree triangle. And at that point, a good chunk of my trigonometry works very nicely. For example, your sine functions, your cosine functions, and your tangent functions, often called SOHCAHTOA. We'll look at that in a moment more, but that's something that works really well on right triangles. Okay, so head-to-head, like in the first problem, works great, add them together, but if they're at right angles, we can use this trigonometry. Since we're at a right triangle right here, I can use the Pythagorean theorem to find this sine, and I can use the trig functions to find this sine, this angle. You're welcome to always just stop the video and try it out. But at this point, we're going to kind of show you how this works. Okay? Now, again, a reminder, what is the direction of this guy? It is going to be this angle, but it's going to be north of the west point. So whatever angle we have, north of west. That's really important. We could also describe this line relative to here. This would be the angle west of north. That's really important too. And you should be able to understand the fact that these two angles will add to 90 degrees. And that will give me the whole corner. You should realize that my x component, or my I component, same thing, is negative. And my j, or my north component, is positive. So later on we'll be doing more of this stuff when adding together different types of vectors that aren't at 90 degrees. And this is pretty important. Okay? Alright, so let's look at the math on this a little closer. Alright, so how do I figure out this line mathematically? Alright, well, first of all, it's just a Pythagorean theorem. 9.2 is my answer. Here's the math. And it's a squared plus b squared equals c squared. A, B, C. This math is considered standard. Like, we don't really teach it. It's considered prior knowledge. So if it isn't, you'll want to see your teacher pretty quickly here. Either way, a squared plus b squared equals c squared. So a is 9, b is 2. Square them both, add them together, square root that value, because I'm going to algebraically get rid of this square value. So square root both sides, and I get 9.2. Again, that math should be relatively understood. If not, you gotta see your teacher and get some help here. All right, so that's 9.2. And then I'm going to use my tangent function to get the angle. Now, once I have all three sides, I can use the sine, cosine, or tangent. You do not have to use the tangent. Okay, I'm using the opposite line and the adjacent line or vectors to get this angle. So tangent is equal to the opposite over the adjacent. So the inverse tangent, again, this is not a tutorial on how to do the functions of trigonometry. So that's not detailed too closely here. So the angle equals the inverse tangent of 2 divided by 9, opposite over the adjacent. 2 divided by 9, and that equals 12.5 degrees. Be careful, if you're not getting 12.5 here, check to make sure your calculator is in degrees and not in radians. Okay. All right. So how would I write this out? I'd write out my vector name is 9.2 miles. That's my magnitude, my new magnitude. Okay, and that's the distance from the origin. The origin is 0, 0. All right. And this one here is 9 and 2. So it'd be 9, 2. That'd be like the Cartesian plane sort of coordinates, 9, 2, and that would be that. Okay, so, but it is 9.2 miles from that origin. And what direction? Well, it's 12.5 degrees north of west. Now, again, you can describe this vector relative to the north line. All right, so to get that, you would just take the 12.5 degrees. I don't know why I don't have 12.5 here, but I'm going to take the 90 minus the 12.5, and I get 9.2 miles, and it's going to be 77.5 degrees. That's west of the north mark. Okay. And that is the basic way in which this works. Okay. Adding two vectors together, forming a vector name. Now it also says here, what is the absolute vector, essentially? Let's try that for a second. Okay. So the absolute is a little bit pretty much the same. Is that rather than measuring your line based off of the west axis or the north axis, we're going to base everything off of the 0, east. So all I do is I want to know what is this particular angle here. And I take the whole thing is 180, so I'm going to subtract off the 180 from 12.5. You'll see that right here. and 167. So pretty simple. So they ask for an absolute vector. They want the whole angle from 167.5. And you'll find that particular vector is useful when we get into some of the more complicated vectors. Okay. Thank you very much. Mr. Schweitzer out.